Hey everybody, welcome to the Nitration Lab. Here's the outline for this video. I'll be covering the reaction and going over the procedure, and during that I'll spend some time talking about column chromatography. Then I'll show the experiment in the lab. This is the reaction that we'll be doing. We'll be taking 4-tert-butyl-phenol and forming the mononitro product and the dinitro product using nitrated silica gel as the reagent. We could use other reagents like sulfuric acid nitric or anhydrous nitric acid, but using nitric acid absorbed on silica gel is a safer and milder method with fewer complications to worry about, so we're going to use that. Here's a look at what happens mechanistically. We have the nitrated silica gel, and the OH group on the phenol is an electron donating group which activates the aromatic ring to nucleophilically attack the nitrogen and form the mononitrated product. Now, on another aromatic ring, that nitro group would be too strongly deactivating to form the dinitrated product, but since there is that OH group, which is an electron donating group, it can activate the ring, helping progress the reaction to form that dinitrated product. So we'll dissolve the 4-tert-butyl-phenol in methylene chloride and add the nitrated silica gel slowly. It can react pretty violently, so we don't want to throw it in all at once. As that's added into the round bottom flask, the solution will turn yellow and eventually a dark orangish color, and we'll let that react at room temperature for about 5 minutes. After which, the remaining silica gel will be filtered through a funnel with a glass wool plug, which will look like this. And we'll need to use glass wool because the very acidic nature of the nitrated silica gel would actually disintegrate normal filter paper, but the glass wool does just fine. When we pour the solution in, the silica gel will gather on top and the methylene chloride solution will run through into the Erlenmeyer flask, and then we can rinse the silica gel with additional methylene chloride to help reclaim more product. We can then start evaporating the solvent, and while that's evaporating, we'll test that both products were formed during the reaction using TLC. So we'll spot the TLC plate and we'll develop it using a 1:1 hexane methylene chloride solution. And this is what it'll kind of look like once it's developed. The two products kind of stain the silica gel as they pass through it, so oftentimes you'll see an orange smear at the bottom, but the two spots on top are for the actual products. Now, we used a pretty nonpolar solvent, half of it being just hexane, and if we look at the molecule, we'd assume that it would be fairly polar with an OH group and a polar nitro group, so it would be safe to assume that it wouldn't move very far in the TLC plate at all, but that's not the case. The alcohol group can actually hydrogen bond with the oxygens on the nitro group that is ortho to it, so that decreases its polarity quite a bit because it's no longer able to hydrogen bond as well with other compounds like the silica gel, so it won't interact with it nearly as much as other alcohol groups that could hydrogen bond with it. The same thing happens with the di product. It's just going to be more polar than the mono product because it does have an additional polar nitro group on it. So if we look back at the TLC plate, that means the top spot would be for the mono product and the bottom spot would be for the di product. And if our TLC plate ends up looking like this, that means both products were formed and we'll separate them later using a column. Then before the solvent is completely evaporated, we'll add some silica gel to the solution, which helps make the products easier to transfer once the methylene chloride is gone. Then the products can be separated using column chromatography. This is what the column will look like. We'll have the mono and di products as a yellowish solid on top of 8 to 10 inches of activated silica gel, which will be the stationary phase and will be what separates the two products throughout the process. We'll elute the column using a 1:1 hexane methylene chloride solution, and as we do so, the column will end up looking like this, where the silica gel gets stained yellow from the two products moving through, meaning that we're not going to see a clear separation between the two products. We just know that both of them are in there somewhere, and we know that the mono product is less polar, so it'll be coming out of the column first. Since we won't be able to distinguish when the di product starts coming out as well, we're going to separate the solution into 10 fractions, gathering about 3 to 4 milliliters of solution in each of those fractions. This will minimize contaminating the mono product once the di product starts coming out of the column. So we'll end up with 10 test tubes, each with about 3.5 milliliters of solution, and we'll test the purity of each of those fractions using TLC. We'll spot TLC plates with each of the fractions and develop them, and they'll end up looking something like this. So the first two fractions would be pure monoproduct. Fraction 3 would have contamination because it contains both products. And fractions 4 through 10 don't show any monoproduct, meaning they have the remaining diproduct that came out last. We can combine all of the fractions that have pure monoproduct into a beaker, and then combine all of the fractions that have pure diproduct into a separate beaker and begin evaporating the solvent. Once that's done, we can characterize the pure products by taking a melting point for the diproduct. We won't take one for the monoproduct because its melting point is right around room temperature, so it'll end up as a liquid, kind of like an oil, and then we can run an IR spec for both. Okay, I'm going to start by weighing out 240 milligrams of 4-tert-butyl-phenol, and I'll add that to a round bottom flask with a spin bar inside. Then I'll add 5 milliliters of methylene chloride to start dissolving the phenol, and it'll take some spinning and probably the full 5 milliliters to make sure that it's completely dissolved. Now I can add 1.5 grams of the nitrated silica gel. And this is pretty reactive, so I'll be adding it slowly, watching for the yellowish orange color that starts to appear, which we can see here, so that's looking good. I'll put on the air condenser and let that reaction continue at room temperature for about 5 minutes. While that's going, I'll set up the glass wool plug, just placing some glass wool into a funnel. Once the reaction has finished, I'll remove the air condenser and can now take the round bottom flask to pour the solution into the funnel. And you can see the stained silica gel gathering on top of the glass wool. I'll rinse the remaining silica gel in the round bottom flask with some additional methylene chloride to help reclaim more product, and then run that solution through the funnel as well. I'm going to rinse it one more time just in case, and you can see that the solution is a lot more dilute, so we're probably good after this. Once I've passed that through the funnel, I'll rinse the silica gel on top of the glass wool with some more methylene chloride just to help push any product through that would have been left over. Then I can start evaporating the methylene chloride solvent off. And while that's going, I'll do a couple of things. I'll first dispose of the remaining silica gel into the desiccant waste. And then I'll also spot a TLC plate with the solution to test that both products were actually formed. I'll develop that TLC plate using the 1:1 hexane methylene chloride solution. And here you can see how the products stain the silica gel as they move through it. But once it's done, we can clearly see that both products were formed, the top spot being for the monoproduct and the bottom spot being for the diproduct, and we'll separate those later on using the column. Before the methylene chloride is completely evaporated, I'll add 500 milligrams of the activated silica gel. And I'll mix it around really well, making sure that the product gathers on it evenly. And I'll make sure that the solvent is completely evaporated, or else it'll interfere with the separation process in the column. It'll end up looking like this once it's done, and now it's ready to be transferred over to the column, so I'll start setting that up. I'll first place some glass wool into the bottom of the column, and then I'll clamp it so that I can add the rest of the components using a funnel. I'll start with some Ottawa sand and just enough to cover the surface area of the column. Then I can add about 8 to 10 inches of the activated silica gel, and while I'm adding it, I'll tap the sides with some vacuum tubing to make sure that it settles evenly. Once enough activated silica gel has been added, the product can then go on top. with some final Ottawa sand to finish it off. And now we're ready to add the eluting solvent, the 1:1 hexane methylene chloride solution, and I'll push that through the column using a bulb. I'll make sure to replenish that solvent before it reaches the Ottawa sand to make sure that the column doesn't run dry. You can see the product staining the silica gel as they move through the column, so we're not going to see any separation between the two products, but we'll gather the solution in 10 aliquots as it comes out. At first, we'll just gather the solvent in a test tube until we start seeing some yellow come out, which means product is coming out now. So we'll start gathering that in a separate test tube, and this will be the first fraction out of the 10. I also have a separate test tube with 3.5 milliliters of water as a reference for how much solution to gather in each fraction. So I'll elute the column until there's about the same amount of solution as there is water in the reference, at which point I can move on to the second test tube now and continue with the exact same process. I'll fill that one until it matches the amount of liquid in the reference and then move on to the third aliquot. Now I'm going to do this for 10 fractions, so I'm not going to show all of them, but as the process goes on, you can see that the column looks more dilute now, as well as do the fractions. This is fraction number 8, and this is the final fraction, fraction 10, which is looking pretty dilute at this point, meaning that most of the product is out now. Once I've gathered all 10 fractions, I can dry the column by just pushing all of the solvent completely through, and I'll gather that solvent in a separate test tube from the others. Now, to dispose of all of the contents of the column, I'll attach a tube of lab air to the bottom of the column and create a seal as best as I can with my hands, aiming it into the desiccant waste. Then someone else will turn on the lab air and it'll blast everything into that waste. Now we have the 10 fractions of the solution gathered from the column, and I'll test the purity of each one individually using TLC. So I'll make 10 spots for each of their respective fractions and develop them using the same solvent as before, the 1:1 hexane methylene chloride solution. Looking at the developed plates, we can see that fractions 1 and 2 can be combined for the mono product, and fractions 4 through 10 can be combined for the di product, and we'll exclude fraction 3 since it contains both. Before combining the fractions for the mono product, I'll weigh out the empty beaker. Since the mono product ends up as a liquid, we can just weigh the beaker again once it's done evaporating. Then I'll also combine the fractions 4 through 10 in a separate beaker for the di product. The solvents can then be evaporated, and we'll see the mono product show up as kind of an oil once it's done, whereas the di product we'll see as a yellow solid, and we can take a melting point for that one. I'm going to start by characterizing the mono product first. I'll weigh out the full beaker, which ends up being 14.966 grams. Then I'll run a neat IR using a capillary tube to spot the TLC plates. And it turned out pretty well. We have the OH peak that we'd expect, plus 2 sharp peaks for the nitro group, one around 1530 and the other around 1320. Let's see how the di product turned out. I'll weigh out the product, starting with the empty watch glass, around 9.736 grams, and then the full watch glass ending up around 9.795 grams. Then I'll measure the melting point range, and it looks like the product started melting around 92.2 degrees Celsius and finished around 94.2 degrees Celsius. And finally, I'll run an IR spec using the neutral mole technique. And it looks like it turned out great as well. We have the alcohol peak and the 2 peaks for the nitro groups. It's obviously going to be very similar to the mono product, so the main distinguishing factor here is going to be the melting point.